Look around you. Feel the gentle, insistent pull that holds you to your chair, that holds the air in the room, that holds the world together. You call it gravity. You have known it your entire life. It was the first force you ever felt, the unseen hand that guided your first stumble, the silent partner in every breath you have ever taken. It is the most familiar, the most constant, the most intimate presence in your existence. And you know nothing about it. Not really. What you think of as a force, a simple pull, is a lie. A convenient story your senses tell you to make sense of the world. The truth is something far stranger, a concept so profound it bends the very meaning of space and time. And hiding within that truth is a ghost, a phantom particle that physicists have sought for a century. A ghost that may be fundamentally, cosmically impossible to find. The search for this ghost, this single particle of gravity, is more than a scientific puzzle. It is a journey to the very edge of reality, to a place where the act of looking at something can destroy it, a place where the universe itself seems to conspire to protect its deepest secret. This is the story of a force that is not a force. It is the story of a particle that may not be a particle. It is the story of the graviton. And it is a story that may change not only how you see the universe, but what it means to see it all. The lie you believe is a simple one, born of human intuition. You see an apple fall from a tree. You feel a pull toward the earth. You conclude that a force is acting upon you, an invisible rope tethering you to the ground. For centuries, this was the height of our understanding, codified by Newton. Gravity was a universal law of attraction, a force that reached across the void to pull objects together. It was a good story. It was a useful story. It allowed us to predict the orbits of planets, to chart the course of comets, to build the modern world. But it was not the truth. The first layer of the illusion was peeled back not with a telescope, but with a thought, an imagination. A man named Einstein imagined falling. He realized that in free fall, you are weightless. The force of gravity seems to disappear entirely. How can a force simply vanish depending on your point of view? A true force, like the push of a hand or the pull of a magnet, does not care how you are moving. It is always there. This simple thought experiment broke the old reality. Gravity was not a force pulling you through space. Gravity was the shape of space itself. This is the first great truth, the revelation of general relativity. The universe is not a static stage on which the drama of existence unfolds. It is an active participant. It is a four-dimensional fabric, a landscape of space-time. And this landscape is not flat. It has curves and hills and valleys, all created by the presence of mass and energy. The Earth is not pulling you down. It is creating a deep valley in the fabric of space-time around it. You are not being pulled. You are simply following the most straightforward path through that curved geometry. You are rolling downhill in space-time. The moon is not being tugged by an invisible rope. It is caught in the Earth's space-time valley, forever rolling around its edge. Mass tells space-time how to curve. Space-time tells mass how to move. It is a cosmic dance, a silent, beautiful conversation between substance and absence, between matter and the void. This was a revolution in thought so complete, so profound, that it redefined the very ground beneath our feet and the stars above our heads. It painted a picture of the cosmos as a grand, geometric sculpture. But it was not the only revolution. At the very same time, in the early decades of the 20th century, another group of pioneers was journeying in the opposite direction. They were not looking at the vastness of the cosmos, but at the infinitesimal heart of the atom. And the world they found was not a beautiful, predictable sculpture. It was chaos. It was a world of shimmering probabilities, of particles that were also waves, of things that existed in multiple places at once until you looked at them. This was the world of quantum mechanics, a place governed not by elegant certainties, but by the stark, cold roll of cosmic dice. Heisenberg, Bohr, Schrödinger, Dirac. They were the oracles of this new, strange domain. They spoke a language of uncertainty, of fundamental limits to what we could ever know. An electron did not have a position. It had a cloud of probability. Energy was not continuous. It came in discrete packets, or quanta. Reality at its smallest scale was not a solid thing. It was a flickering, ghostly, statistical dream. For a time, these two revolutions could exist in their own realms. General relativity was the law of the very large, of planets, stars, and galaxies. Quantum mechanics was the law of the very small, of atoms, electrons, and photons. They were like two magnificent kingdoms with a vast, unexplored territory between them. But physics craves unity. It seeks a single story, a single set of rules that governs everything, from the fall of an apple to the birth of a universe, from the dance of galaxies to the flicker of a single particle. And so, the quest began to merge these two worlds. The quest for a theory of quantum gravity. The path seemed clear, if challenging. The quantum pioneers had already succeeded in a similar quest. They had taken the classical theory of electromagnetism, the force of light and magnets, and they had quantized it. They found that the electromagnetic field was not a smooth, continuous thing. It was made of discrete packets of energy, tiny messenger particles. They called this particle the photon. When a magnet attracts a piece of iron, it is because they are exchanging a storm of invisible photons. When you see light from a distant star, it is because photons have traveled across the universe to strike your eye. The force was revealed to be a conversation, an exchange of these quantum messengers. This triumph was repeated. The weak nuclear force, which governs radioactive decay, was found to be carried by its own messenger particles, the W and Z bosons. The strong nuclear force, which binds the nucleus of every atom together, was found to be carried by gluons. The pattern seemed undeniable. 3 of the 4 fundamental forces of nature were quantum conversations, carried on the backs of messenger particles. Surely, gravity must be the same. This was the birth of the idea, the birth of the ghost. If Einstein's spacetime is the field, then it too must be quantized. It must be made of discrete packets. There must be a fundamental unit of gravity, a messenger particle that carries the information of spacetime's curvature. They gave a name before they ever found it, a name born of hope and logical expectation. The graviton. In this new picture, the dance between mass and spacetime becomes a blizzard of these phantom particles. The Earth and the Sun are not just sitting in a static, curved geometry. They are locked in a furious, unending exchange of gravitons, constantly telling each other where they are and how to move. Every atom in your body is, at this very moment, broadcasting gravitons, whispering its existence to the rest of the universe. And it is receiving them, listening to the gravitational song of the cosmos. It was a beautiful idea, a necessary idea. It was the missing piece of the puzzle, the key to a final theory of everything. But when physicists tried to write the equations for it, reality broke. The math screamed. The elegant poetry of general relativity and the strange grammar of quantum mechanics refused to speak to one another. When they were forced together, the calculations did not just fail, they exploded into nonsense. They yielded infinities, answers that signified a complete breakdown of the theory. It was the first great sign that something was deeply, fundamentally different about gravity. The initial paradox was a mathematical one. The interaction of a graviton with other particles, including other gravitons, created unstoppable feedback loops in the equations. The smooth, gentle curvature of Einstein's universe became a jagged, chaotic mess at the quantum level. The fabric of space-time, when looked at too closely, seemed to tear itself apart. This was not just a difficult problem. It was a crisis in the heart of physics. The two pillars of our modern understanding of reality were, it seemed, built on incompatible foundations. One described a smooth, deterministic, geometric world. The other described a pixelated, probabilistic, chaotic world. And there was no bridge between them. But the dream of the graviton did not die. Hope shifted from pure mathematics to the possibility of experiment. If we could just detect one, just a single one, it would prove the principle was right, even if the math was wrong. We could capture the ghost and force it to tell us its secrets. So, what is this phantom we are hunting? What are its theoretical properties? The graviton, if it exists, must be a strange creature indeed. Like the photon, it must be massless. This is because gravity, like light, has an infinite range. The gravitational influence of the sun reaches across the solar system and beyond, so its messenger must be able to travel forever without decaying. Being massless means it must also travel at the ultimate cosmic speed limit, the speed of light. When gravitational waves were first detected in 2015 by LIGO, this prediction was confirmed. These ripples in space-time, themselves a classical manifestation of gravity, traveled at the speed of light. It was a powerful, albeit indirect, piece of evidence, a shadow on the cave wall that hinted at the shape of the thing casting it. But its most important property is more abstract. It is called spin. You can think of a particle's spin as its fundamental nature in an interaction. A photon, the carrier of electromagnetism, has a spin of 1. This means that it can be either attractive or repulsive. Like charges repel, opposite charges attract. It is a one-dimensional interaction, a simple push or pull. The graviton, however, must have a spin of 2. What does that mean? It means gravity is different. Gravity only attracts. There is no such thing as negative mass to repel it. A spin-2 interaction is not a simple push or pull. It is a stretch and a squeeze. It is a tidal force. Imagine a ripple passing through the fabric of space-time. As it passes, it stretches space in one direction while squeezing it in the perpendicular direction. This is the unique signature of gravity. It is not a force in space-time. It is a distortion of space-time. Its messenger particle, the graviton, must therefore be a quantum of space-time distortion itself. A tiny, propagating ripple of pure geometry. The rules of this unseen world are elegant in their conception. The entire universe, every particle, every star, every galaxy, is engaged in a constant, silent conversation. Every object with mass or energy acts as a transmitter, ceaselessly broadcasting gravitons in all directions. These gravitons are the messengers, carrying the news of that object's presence. When another object receives these gravitons, it is informed of the other's existence, and its motion is altered accordingly. It follows the path dictated by this incoming stream of geometric information. It is a universe of pure information exchange. The curvature of space-time is not a static property. It is a live, dynamic network, updated at the speed of light by this storm of graviton messengers. You're not just sitting on a planet held by gravity. You are participating in an unimaginably vast and complex quantum computation that defines the shape of your reality from moment to moment. This is the theory. This is the ghost in the machine. But how do you prove it? How do you catch a ghost? The experimental evidence is sparse, almost non-existent. We have detected gravitational waves, yes, but a gravitational wave is not a single graviton. A wave of light is composed of trillions upon trillions of photons. A gravitational wave, a ripple from 2 colliding black holes, is thought to be composed of an even more mind-boggling number of coherent gravitons. Detecting a gravitational wave is like feeling the collective roar of a stadium. Detecting a single graviton is like trying to hear the whisper of a single person in that same stadium during the loudest cheer. The problem is one of weakness. Gravity is, by an astonishing margin, the weakest of the 4 forces. The electromagnetic force holding an electron to a proton in a hydrogen atom is about 10 to the power of 36 times stronger than the gravitational force between them. That is a 1 followed by 36 zeros. This unimaginable weakness means that individual gravitons interact with matter so rarely, so feebly, that the chance of one stopping in any conceivable detector is practically zero. A graviton from the sun could travel through light years of solid lead with almost no chance of being stopped. We are swimming in an ocean of gravitons, yet we are completely transparent to them. They pass through us, through the Earth, through everything, as if we were not there. They're the ultimate ghosts, leaving no trace of their passage. So, the challenge becomes clear. To have any hope of detecting a single graviton, you need two things. You need an incredibly intense source of gravitons, and you need an incredibly sensitive, massive detector. And this is where the story turns from merely difficult to deeply paradoxical. This is where the universe begins to play its cruelest trick. The journey into this paradox was charted by brilliant minds, most notably through thought experiments inspired by the physicist Freeman Dyson. They asked a simple question: what would it take in principle to build a graviton detector? Let us forget about engineering challenges and budget limitations. Let's assume we have access to all the matter and energy in the universe. What do the laws of physics themselves demand? The logic begins simply enough. To detect a particle, you must make it interact. To make a graviton interact, you need a detector with an immense amount of mass packed into a dense area. The more mass, the higher the probability that a passing graviton will notice it and leave a signal. So, you start building your detector. You gather stars. You crush them down into a hyperdense sphere. You have created an object with an immense gravitational field, a perfect target for a passing graviton. Now, you need a source. You need high-energy gravitons, as they are more likely to interact. How do you get high-energy gravitons? The same way you get high-energy photons. You smash particles together at incredible speeds in a colossal particle accelerator. So you build one. Let's say it wraps around the entire solar system. You accelerate protons to near the speed of light and collide them. Most of the time, this produces a shower of familiar particles. But very, very rarely, the collision should produce a high-energy graviton. You have your source. You have your detector. You aim the beam from your accelerator at your hypermassive detector and wait. This is where the first ghost of quantum mechanics appears: the Heisenberg uncertainty principle. The uncertainty principle is a fundamental law of nature. It states that there is a trade-off in what you can know about a particle. The more precisely you know its position, the less precisely you can know its momentum, and vice versa. It also applies to energy and time. The more precisely you know the timing of an event, the less precisely you can know the energy involved. To detect your graviton, you need to pinpoint its arrival at your detector. You need to know when it hit and where it hit with some degree of precision. Otherwise, you cannot distinguish its signal from the background noise of the universe. According to the uncertainty principle, to know the timing of the graviton's impact with high precision, there must be a large uncertainty in the energy exchange during the collision. To know the location of the impact with high precision, there must be a large uncertainty in its momentum. This means your collision must be incredibly energetic to produce a graviton that is detectable in this sense. So, you crank up the power on your solar system-sized accelerator. You are producing gravitons of higher and higher energy. Now, we return to your detector, this hyperdense sphere of crushed stars. You need to make sure your detector is sensitive enough to register the tiny kick from a single graviton. This means the components of your detector, its atoms, must be very precisely located. Their positions must be known. But the uncertainty principle rears its head again. If you know the positions of the atoms in your detector with great precision, you must be fundamentally uncertain about their momentum. They will be jiggling and vibrating uncontrollably. This quantum jitter would overwhelm the tiny signal from any graviton. There is only one way to solve this. According to the laws of physics, the only way to reduce this quantum jitter is to make the detector even more massive. By making it heavier, you make it harder to move, more resistant to the quantum jitters. The logic is now closing in on itself like a loop. To detect a graviton, you need high energy. To get high energy, you need to smash particles with immense force. To receive the signal, You need a detector that is incredibly massive and dense. This is the setup. The most powerful accelerator imaginable, firing at the most massive detector imaginable. And here, we arrive at the heart of the paradox. Here, we violate not just classical logic, but the very possibility of knowledge. Let's look at your detector again. It is an object of immense mass, concentrated in a certain region of space. Einstein's theory of general relativity tells us that any concentration of mass or energy curves spacetime. The more you concentrate, the steeper the curve. There is a point of no return. For any given mass, there is a radius called the Schwarzschild radius. If you squeeze that mass down into a sphere smaller than its Schwarzschild radius, the curvature of spacetime around it becomes infinitely steep. The escape velocity from its surface exceeds the speed of light. Nothing, not even light, can escape. You have created a black hole. Now, let's revisit the requirements for our experiment. You need to fire a high-energy graviton, but energy is equivalent to mass. Einstein told us this. E equals mc squared. A high-energy graviton carries with it a significant equivalent mass. You fire this high-energy particle at your hypermassive detector. The logic of the thought experiment, when you run the full calculation, is as follows. In order for your detector to be massive enough and your graviton energetic enough to guarantee a detection event within a reasonable time frame, say, the age of the universe, a fatal condition is met. The combined energy of the graviton and the detector, concentrated in the small region of space-time where the interaction would occur, is enough to push that region below its own Schwarzschild radius. The act of measurement itself creates a black hole. The very event you were trying to observe, the absorption of the graviton by the detector, triggers the formation of an event horizon that shrouds the entire experiment. The information you sought is instantly and irrevocably trapped inside, sealed away from the rest of the universe forever. Your detector swallows the particle it was built to find, and then it swallows itself. The experiment is destroyed by the very conditions required for its success. Let this sink in. This is not an engineering problem. This is not a matter of building a better detector. This is a fundamental limit imposed by the laws of physics themselves. The universe seems to have woven a conspiracy into its very fabric. It has created a rule. Thou shalt not observe a single graviton. The role of the observer, a ghostly presence in standard quantum mechanics, becomes the executioner here. In the famous double-slit experiment, observing which slit a particle goes through forces it to behave like a particle instead of a wave. The observation changes the outcome. But here, the consequence is infinitely more profound. The observation does not just change the outcome. It eliminates the possibility of there being an outcome that can be known. It wraps the question in a shroud of pure nothingness. Nature refuses to show you its smallest gear, and it enforces this refusal with its most extreme creation, the black hole. What does this mean? What does it mean if the fundamental particle of the most ubiquitous force is, in principle, unseeable? This is where physics bleeds into philosophy. We are forced to confront the question of what it means for something to be real. We have always operated under a simple assumption. A thing is real if you can, in principle, touch it, see it, measure it. A thing is real if it leaves a mark on your instruments. The electron is real. We could track its path in a cloud chamber. The photon is real. We can count individual ones with sensitive cameras. The Higgs boson is real. We saw the signature of its decay in the Large Hadron Collider. But the graviton? It seems to exist in a different category of reality. It is a concept that is mathematically necessary to reconcile our two greatest theories. It is a ghost whose presence is implied by the logical structure of the house, but who can never be caught on camera. Does a particle that cannot be detected deserve to be called real? Or is it merely a placeholder in our equations? A symbol for our own ignorance? Is the universe telling us that our entire approach is wrong? That gravity is simply not a force like the others, and our attempt to quantize it, to break it into little bits, is as foolish as trying to find the fundamental particle of love or justice. Perhaps space-time is not fundamental at all. Perhaps it is an emergent property, like the wetness of water. A single molecule of H2O is not wet, but put enough of them together, and the property of wetness emerges from their collective interactions. Perhaps space-time, and gravity along with it, emerges from a deeper, stranger layer of reality, a network of pure quantum information that has nothing to do with geometry. In this view, the graviton is not a fundamental particle, but a ripple in this emergent fabric, a collective excitation that can never be isolated from a whole. This paradox forces us to look at ourselves, the observers. You're a creature of mass and energy. You are held together by quantum forces, and you are held to the earth by gravity. The standard model of particle physics describes the particles that make you. General relativity describes the stage on which you exist. But if the graviton is the messenger of gravity, then you are not just a passive object being acted upon. You are an active participant in the gravitational field. Every time your heart beats, the movement of blood, tiny as it is, sends infinitesimal gravitational ripples, gravitons, out into the cosmos. Every thought in your brain, an electrical signal that is a movement of charged particles, broadcasts its existence via gravity. You are built from the particles described by quantum mechanics. You are, in a very real sense, a collection of quantum fields, a complex, stable resonance in the chaotic quantum foam. And you're speaking the language of gravity. You are broadcasting your existence into the fabric of space-time with every breath. You are a whisper in the cosmic opera, a constant stream of gravitons announcing your presence to the universe. You are built from quantum ghosts, and you're speaking with ghosts. This connection redefines your place in the universe. You are not separate from the geometry of space-time. You are part of its conversation. The line between you and the cosmos dissolves. The ancient spiritual idea of being one with the universe finds a strange, precise, and physical echo in these modern theories. You are literally woven into the fabric of reality through an unceasing, unseeable quantum exchange. But what of the observer paradox? What if the barrier between observation and reality is more fundamental than we ever thought? We have reached a point where asking a question about the universe can fundamentally change it, or even create a part of it, like a black hole, that prevents an answer. This suggests a terrifying and exhilarating possibility. Perhaps the strict separation between the observer and the observed is the ultimate illusion. Could it be that consciousness itself, the very act of being an aware observer, is not an accidental byproduct of biology, but a fundamental aspect of the universe's physics? This is a highly speculative leap, a step beyond the bounds of accepted science. But in the face of such profound paradoxes, we are forced to ask profound questions. What if the universe, in some way, requires an observer to become fully real? What if reality is a participatory process, a dialogue between consciousness and the quantum substrate? In this view, the measurement problem is not a problem at all. It is the signature of creation itself. It is the moment a wave of potentiality collapses into a single, concrete actuality, guided by the act of observation. Perhaps the reason we cannot see a single graviton is that gravity is the framework of the observation itself. It is the context, not the content. Trying to observe a graviton might be like trying to make your eye see itself without a mirror. The tool is not suited for the task because the tool is the thing it is trying to investigate. We began this journey seeking a particle, a thing, a neat, quantifiable answer to a puzzle. We asked how we find the graviton, but the journey has led us to a different place. The universe has answered our question with a riddle, wrapped in a paradox, sealed by a black hole. It has shown us a place where our questions themselves seem to break the world they are trying to describe. And so, we must return to the central question, but reframe it with the humility we have learned. Is the graviton real? Perhaps the question is meaningless. Perhaps it is a word for a process, not a thing. Perhaps it is the verb of the universe, not its noun. It is the curving of space-time, not the thing that curves. It is the whisper of geometry, a whisper that can only be heard as a chorus, never as a solo voice. The quest for quantum gravity is not a failure. The inability to detect a graviton is not a dead end. It is a profound discovery in its own right. It is the universe showing us the limits of our intuition. It is nature telling us that its deepest layers are not just smaller versions of the world we see. They're a different kind of reality altogether, one that may not be built of things at all. The final metaphor, then, is not one of a particle, but of a language. The universe is a story it tells itself. The laws of physics are the grammar of that story. The particles are the words. For a long time, we thought we could isolate every word and define it. But now we have found a word, the graviton, that seems to have no meaning in isolation. Its meaning only exists within the full sentence, the full paragraph, the grand narrative of space-time. Trying to capture a single graviton is like trying to capture the meaning of a story by cutting out a single you do not get the meaning. You just get a meaningless scrap of paper, and you have damaged the story in the process. And so you stand here at the end of this journey, still feeling the familiar pull of gravity. But it is no longer simple. It is no longer a mere force. It is the poetry of the cosmos. It is the silent, unseeable, unknowable conversation that binds you to the earth to the sun, and the sun to the spiraling arms of the Milky Way. It is a mystery that deepens the more we explore it, a question that becomes more beautiful for being, perhaps, fundamentally unanswerable. You're a part of that poem. You're a part of that question. And living within that mystery, feeling its constant, silent presence, is a form of understanding far deeper than any single answer could ever provide. The ghost remains a ghost. And perhaps that is the most profound truth of all.